In this part of lecture, we are trying to write down all calculations, and we are going to try to update our weights and to make this supervised learning task by minimizing loss. So first of all, let's define in our class calculations of neural network, because we've just defined that we have some weights, but if we are approaching real neural networks, then if we have some outputs, if we have some inputs, then we can calculate these outputs directly by using fact that how neuron works, that its output is equal to activation function, which will be sigmoid from sum of weights multiplied by inputs of neurons. So then we are going to connect all these neurons with connections, and we will already define weights, so we can jump right into code and see so this is calculation, and here we go. So first of all, we need to find a way to calculate values of a new layer, of the next layer, if we have inputs of input layer. So if we are talking about, so first we are going to calculate values of hidden layers, and then we can apply the same algorithm to calculate from treating hidden layer as input layer, we can calculate output layer. So we can do this. Here we generate our weights, our random weights, and then we have some random input. And here's a little code how we calculate output if we have two-layer system. So we just first we have some summation, then we sum products, and then we apply sigmoid function and append this to output list. And here's output or results that hidden neurons will have. And then we can apply the same algorithm, but instead of x, we'll have y, and then we can calculate, for example, z, which will be defined as outputs of output neurons. So here we have this part of code, and this function will be called y, and we need self, and self means that we need object itself, object neural network, and we have input, which is called x. And input x is a list, so first we apply and find hidden values, and then we apply the same for output values and return output values. So again, we initialize our random neural net with the same parameters and print input. If we have we print input, which is equal to 1, 0, 1, and then we print output, which is equal to these numbers. And you can see that number of neurons in output layer is the same as number of these results in list. And finally, after we've defined how to calculate output of neural net from input, we can go back to supervised learning and And we can remember then that we have 3 tasks. The first one is to define loss function, which is judging how bad or good this neural network for given data. So first task number 0 is to get data, and this task will be is quite easy. Then we have that loss function, which will be denoted as capital L, is basically a function which depends on weights. And by the way, we were talking about weights from input layer to hidden layer. We will denote this table as A. And if we're talking about weights between hidden layer and output layer, we will denote this table as B for simplicity. So we have this loss function, and it has a lot of parameters because, for example, if we have 3 inputs, 4 hidden neurons and 2 outputs, then number of weights is equal to 20, and it's equal to number of parameters of loss function. And we need to somehow define this loss function. So if we have some data, and that means that we have some lists x and y, and these are data, so we have x values and y values. We can define loss function as sum over all output neurons, and here we have 1/2 of difference between output neuron value minus desired one. So we will denote data points as x with a hat and y with a hat, and in square. And this is called squared mean error. And so we have, after we've calculated, after we have some x1 and x2, we get some y1, y2, y3, and then we compare them with data points, which will be denoted as y1 with a hat, y3 with a hat. Then we take a difference and square them and sum. And that basically shows how fit neural network for this data point. And the same can be done for a lot of data points, which we are going to just repetitively do for different data points. So that's how we defined loss function. What's next? We have to minimize loss function. So we try to loss function to be minimal. And you can remember from previous lectures that we talked about gradient descent, and right now it's perfect for that, for neural networks, because we have a multivariable function with several variables, like 20 or even more, and we try to minimize it. And you can remember that if we are applying gradient descent, then we are trying to change these parameters like follows. For example, we have some parameter, some weight, and in Python it will look like that. Some number eta multiplied by partial derivative of loss function with respect to this weight. And this is basically whole description of vanilla gradient descent. And this eta is called learning rate, you can remember. And basically it says that we are moving parameters in such a way that loss function is decreasing the most. And that's how we will update iteratively all these weights. So for all weights, like EG or GE, JK, we will have a lot of matrices, a lot of tables. We update each weight like follows. And so we have loss function, it's totally defined. We have that data points, and we can calculate y, because we've just created in class neural net, we've created basically a function which can output of neural net, which can give you output of neural network based on its input. We've just created this. So we have this done, this is done, because this is just data points. And that's how we will update weights. And here's a big question. How to calculate these partial derivatives? And this is the most problem, and we will talk mostly on this lesson about this problem and how to calculate partial derivatives. So I will try to minimize number of complex math to as much as possible. So let's start from the simplest case, from neural network without hidden layer. We have neural network. Without hidden layer. So we have inputs, and this can be, these are just a list in Python or a vector code, and these are outputs. And we know how to calculate these outputs. And this is called y value. And we have desired value. So this is data point. And we want these output values, y1 and y2, to be y1 with the head and y2 with the head. So, and we define loss function as a sum of 1/2 . And now we need to find and by y, so now we are introducing some indices, and we will indices of this layer will be called y, and indices of this layer will be j. So in that case, we are summing by index j, and this weight means in Python list of lists with index y and j. So we are first dealing with connections which are going from neuron y into neuron j. From y to j, and here we have y weight ij. So that's our denotions. So we can choose, for example, for simplicity, this weight and denote it as y ij, wij. So now we need to apply chain rule, which was discussed in 4th lecture, and it basically says that this derivative can be expressed as following. So we can introduce any variable s, which depends on something, and derivative of loss function with respect to this variable multiplied by derivative of this variable with respect to this weight will be equal to partial derivative of loss with respect to weight. So this is chain rule, and we are going to use it. And to calculate it as quick as possible, we'll use, instead of s, following variables. So first of all, we are going to calculate partial derivative of loss with respect to yj. Because it's just in brackets and it's quite easy to calculate. Then we need to calculate partial derivative of yj with respect to this weight. So this means how this weight affects this particular neuron. So that's how we are step by step are going to deal with this problem. So first of all, we need to find this. We can see that yj is, it can be rewritten as y1 So that's how I rewrote it, and you can see that ij is included only in these brackets, and all other values can be treated as constants. And that means that we can only differentiate this simple expression, and then we get exactly this partial derivative. This is going to be just yj minus desired output. So that's first one that we want to keep. We found this. Now we need to find how input of neuron J is affected by this particular weight. Because, to be honest, this neuron is affected not only by that value, but also by that. And that can mean that can be a bit complicated, but still we can figure it out, understanding how do we calculate this yj. So we again use definition of neuron, how it works, and we apply sigmoid function to sum of inputs and we sum by all inputs. So all inputs apply some products to these neurons, then we sum these products, and then we squash it using activation function. So let's rewrite this as S, this sum as S, sum, and then we can a bit rewrite this expression, again using chain rule second time. So we will calculate partial derivative of input, this input to sum j, and then we need to calculate partial derivative of sum j with respect to this weight. This is sum j. So that was found, and now we can just rewrite yj as follows. We can rewrite this whole definition of neuron like that, sum j. And that means that partial derivative, that yj depends only on sum, and that means that partial derivative can be just rewritten as usual derivative, and that means that this is equal to derivative of activation function with respect to sum j. So this is just a derivative of activation function. And then we remember that we use sigmoid function. So we restrict backpropagation algorithm only to sigma function or sigmoid function or logistic function, but at the same time all this chain rules that was written before is still applicable to different activation function. You can still use it with tangent, with ReLU, but you need to think yourself and do the same calculations, but with different activation functions. So yj is just equal to 1 over 1 plus y e to the power sum j. And finally, that's why I've given you as a derivative task this particular function. And you can see that derivative with respect to sum j is just equal to product of yj minus yj, of product yj by 1 minus yj. And that's understandable because if we look at graph of sigmoid function, we can see that if sigmoid function its value is equal to 0 or 1, then this expression is converging to 0, and then function becomes more steeper and steeper, and its derivative is close to 0. But if we have yj is equal to 0.5, then this derivative gains its maximum and it's equal 1.25. So now we can rewrite this as just yj by yj. So partial derivative of yj with respect to this sum is equal to yj multiplied by 1 minus yj. This is the third one. And finally, this partial derivative of sum j with respect to this weight. Let's write it here. So we can again use this trick as we used in loss function, where we just rewrite this sum notation as follows: x1 multiplied by 1j plus x2 multiplied by 2j plus xy multiplied by yij plus further xn multiplied by w and j. And you can see that all other variables are just constants, and we are taking partial derivative with respect to yj, and that's why all variables can be treated as constants. And we can see this partial derivative will be just equal to partial derivative of this simple expression. And as we have x multiplied by some constant, so this will be just a constant, xy. So this can be rewritten as xy. This can be rewritten as yj minus yj with a hat. And that's it. So if we have a neural network with 2 layers without hidden, then we can assign some random values to a weight, and then we can calculate partial derivative of loss with respect to each weight, and then we can update each weight using a gradient descent. And again, to repeat, this is output of J output neuron. This is input of Y input neuron, and this is desired output of J neuron. So if we have data and we can calculate Yj based on x, y, and other axes, then we can calculate this partial derivative, and then we can update each weight using gradient descent. So this formula, remember it, because not remember, but don't forget this time, because you will need to implement neural network, but without a hidden layer. So you are going to make a simpler task. But if you can do it using this formula, then you can train this neural network without a hidden layer, and you'll see that without a hidden layer, neural network performs much poorly. So if you can do this, then you'll understand and derivation of partial derivatives with a neural network with hidden layers. And now we are considering a neural net with hidden layers. But I don't want to give a full explanation, and a full explanation will be in PDF file, which will be in the same GitHub directory. But this explanation has some crucial moments which you need to understand. So if we are considering these weights, which affect connection between hidden and output layer, then it's basically the same task, because loss function can be defined as a sum of desired as a square error, and that means that it directly is affected by these values, and these values are directly affected by this connection. So you're doing chain rule again, and you get the same result. But if we are talking about this connection between input layer and a hidden layer, then it gets much trickier, because, for example, this connection, it affects this neuron. But this neuron, it affects then both neurons, both output neurons, which directly affect loss function, because each hidden neuron is connected with both output neurons. So that means that if you want to calculate partial derivative of loss with respect to these weights from this table of connection between input and hidden layer, then you need to consider how it affects this neuron, and then sum of all these effects. And you can see that we can simplify this algorithm by introducing special variable, which we will call delta. And this delta will be defined as follows. So if delta for special neuron J. And if J is an output neuron, then we get the same results that we get 10 minutes ago using chain rule. And we get that it's just equal to yj minus desired input multiplied by yj multiplied by y if j is an output. But if j is a hidden layer, then it becomes like that. Sum of k, delta k, and I'll explain then what k means, multiplied by weight jk. And again, we have if j is a hidden neuron. So this is expression, and what does k means? K means delta with respect to the next layer. So if we can easily calculate delta j for an output neuron because it's a common expression, and we can just calculate yj, and then we can apply this line to calculate delta j. So for this layer we calculate delta j. And then, with respect to this layer, if we want to calculate its delta j, we need to treat this delta j as delta k. So now, after we've calculated this delta j, we are using this result to calculate it recursively in this layer. And it's done by summing delta k multiplied by weights. And weights are defined from j neuron to the k neuron. So that means that firstly we need to calculate j with respect to an output neuron, then to a hidden using previously calculated delta j. And if we have more than one hidden layer, then we can continue this algorithm by using new delta k. For example, we have two hidden layers. In that case, we calculate delta j. Then we use this to calculate new delta j, which will depend on delta j previous or delta k. So this delta j becomes delta k for the next layer or previous layer if we are considering this direction. And then if we want to calculate this delta j, we need to use this one, delta j calculated, which means that when we calculate just y values, values are going in this direction. But when we are calculating error, error is going in this direction. So we first need to calculate this, this list of values, then we calculate this one and this one. And then all partial derivatives can be very easily written as just delta j multiplied by input y. And this input is an input from a previous layer. So if we are calculating, for example, so we've calculated delta j for this output layer. Then we use it as a delta k for this layer. And then we calculate partial derivatives by multiplying this delta j on these values. This is xy. And this can be done for each table of weights. And finally, we get to this table where we multiplied this delta j on our initial inputs. And that's how backpropagation works. And it's quite complicated, you know. And if you still don't understand, then you can maybe better understand if you look at code. So let's try. So this is how about gradient descent at loss function. So here we go with class neural net. Here we have y function again, and then function train. So first of all, we need x data and y data. Numbers of x data and y data can be different, and that's why we can have a list of lists. So for each x and y data value, we are computing these partial derivatives, and we are adjusting and tweaking these weights. So first of all, you can see that if we're using delta j, we need to calculate inputs of previous layers, and that means that we need to, here we calculate delta j, but we also need a value of a previous layer. And sometimes this layer will be a hidden one, and that's why we need to, that's why we care not only about this final output, but also about output of all neurons. So there we just calculate output of every neuron. This is hidden neuron, this is output neuron. And then we use delta, this is delta j and delta k. So first we calculate delta k. This is for connection between hidden and output neurons. And this is just equal to this formula. So we compare output values with desired y data. So we gave neural network some y data to train on. Now we subtract it, multiply by output, and multiply by 1 minus output. So here formula is quite simple because k is an output neuron. And now we calculate delta j, and this is for connection between inner input and hidden neurons. So here, first of all, we have some summation, and then we multiply delta k by weights between j and k, which means we multiply by weights between hidden neurons and output neurons. And then we use the same formula that we have sum multiplied by hidden value multiplied by 1 minus hidden value. And finally, we see that now we can have a loop through a j values and the k values, and here we have list of weights between hidden neurons and output neurons, and we just subtract some eta, multiplied by delta, and multiplied it by hidden value. And hidden value plays a role of previous value if we are looking in respect from an output layer. And the same goes for table of weights between input layer and the hidden layer. Eta multiplied by delta j with respect to hidden layer and multiplied by input layer. So now let's try to train this neural net on tables of logics. Tables of logic operators, and you can remember that they probably were at the first lesson, that if we have AND operator x and y, and we have x, it's denoted as x1, x2, x1, x2. So logic table for logic operator AND looks like 0, 0 gives 0. And here we can clearly see that it's input. This is input. And this is output. So in that case, we have two inputs, which means that we must have two input neurons. And we have one output, x1 and x2, which means that we have only one output neuron. And between that, we can have as many hidden layers and as many hidden neurons as we want. And if we go more and more hidden neurons, then neural net can compute more sophisticated behaviors. But at the same time, if we have a lot of hidden neurons for such simple logic operator, then this is quite bad, and we will talk about on the next lesson. But right now you can go with number of hidden neurons as much as you want, and then you can construct neural net using class neural net and train it using this data. And this data will be presented in such way. So first we have X data, and this will be a list of lists, a list of X points. This is X data, and Y data will be 0, 0, 0, and 1. And it's important for Y data to be a list of lists, despite that we have only one input and we can just write it as a list, but we still need to write it as a list of lists, because otherwise there might be an error. So here we have a XOR logic operator, here we have a data, here we have this X data and Y data written in form of lists of lists. Finally, we have learning rate is equal to 1, and we just train neural net using following syntax on X data and Y data and eta, and each 1,000 operations we write down how neural net competes with real desired values. So here we have, this is a random initialization, and we can see that because our weights are close to 0, neural net will give you results close to 1.5. And we can see that it's quite bad at modeling XOR operator. And after 1,000 operations, it becomes a bit better. But still, here we have a problem, and it's even bigger than half. But after 2,000 operations, it becomes better and better. And eventually, we have this major improvement after 4,000 operations. And then we have, after 10,000 operations, that if we have a desired input 0, it's very close to 0, 0 and 1, 1, 7. And if we want 1, then we get pretty much 1. So it's really working, and you can now use this class to build up your neural networks and train them, but still you need to have some homework. So your main homework will be to implement this neural network without hidden layer, because it will improve your understanding of backpropagation and how neural networks works. And then you need to train your new neural network without hidden layer and compare it with a neural network with hidden layer. And you'll see which is better and why we use neural networks with hidden layers. So I think that's it. And in the next lesson, we will talk about how to improve computational power of neural networks and what problems you might encounter while training them. So I think that's it, and goodbye.